Okay, so our next speaker is Andreas Kreisel from Niels Bohr Institute. You can start, Andreas, whenever you're ready.
Yes, yeah, thank you, Shantanu, for the introduction, and I thank the organizers for giving me the opportunity to talk about this topic, which is a little bit distinct from Kagome systems, because I will be talking about ultranodal states in multiband superconductors, and I will explain to you a little bit about microscopic origins and come to some experimental probes. And this is kind of a summary of a couple of papers we wrote in the last couple of years. Okay, let me start to explain what the ultranodal superconducting state is. So in one sentence, it's a superconducting state with regions of zero energy quasi-particle excitations of the same dimensionality as the Fermi surface. So let's step back and try to understand this. So to start with just a three-dimensional Fermi surface, then the Fermi surface itself is just an area. And if you now think about different types of superconductors, so the first one, if you have a fully gapped superconductor, so some S-wave state, so all Fermi surface is gapped, no states at zero energy, so no states at all at zero energy. If you think about point nodes, then the space of quasi-particle excitations with zero energy is just zero-dimensional. So here is just one single point, and maybe also some the other side of the sphere that has a zero energy excitation. So this is, for example, a p-wave state, so B2U in some uranium telluride as an example. Now, if you have line nodes, then the zero energy excitations are on one-dimensional on these lines. So this is, for example, in a D-wave superconductor. There might be also similar properties of line nodes in an F-wave state, where you have a line node and additionally point nodes on the poles. But this is all lower dimensionality than the Fermi surface, so 1D, 0D, or no. However, for the ultranodal state, we have surfaces of zero energy excitations, which are really surfaces. So this is an example of regions with zero energy excitations that is discussed in this work in a superconductor where you pair J equals 3 half particles and add a time reversal symmetry breaking. Now, what does this mean? Kind of if you go one dimensionality lower, so if your Fermi surface is just two-dimensional, it's basically the same. If you have a full gap, there is no zero energy excitation. If you have a D-wave state, then you have point nodes, which is zero-dimensional. However, the ultranodal state, you really have lines of zero energy excitations, which is here now shown in some example, which we have discussed. So now again, here the Fermi surface is the red region, which is just some Fermi surface inspired from iron-based superconductors for some reasons that I will explain later. And the ultranodal state has these Bogoliubov Fermi surfaces which form close by to the original Fermi surface. Okay, so far to what it is. Now, why is it interesting? Why is it exotic? So there are some unusual thermodynamic properties. And namely, this ultranodal state has some properties which are usually only known for a normal metal, because we have a lot of zero energy quasi-particles, and therefore density of states looks quite differently. So let me just go through this quickly. So if you have a full gap, then you have no density of states until you reach the coherence peak in the superconducting state. So the density of states is just scales at zero. If you have a point node, then the low energy density of states scales as energy squared. If you have line nodes, then the low energy density of states scales linearly with energy, notably as for example, for the D-wave superconductor. But in the ultranodal state, where you have two-dimensional quasi-particle excitations, then the density of states at zero energy is actually a constant. And that has some imprints on thermodynamic properties, which depend on the properties or lower energy properties of the density of states. And these Bogoliubov Fermi surfaces are actually also protected by symmetries. The symmetries which I will discuss in a second. Now, as I said, this exotic phase is protected by discrete symmetries. And the key quantity is the so-called Pfaffian, which is the sign of the determinant of the Hamiltonian, which is in a sense a Z2 topological invariant. So either it is a +1 or -1. If it's +1, then it's just a trivial superconductor, fully gapped or nodal, and so on. If it's -1, then you really have to have these crossings of the quasi-particle bands through the Fermi level, and you obtain this ultranodal state with Bogoliubov Fermi surfaces. And to test this, one has to look for the sign change of these Pfaffians to see that there is actually this touching. So in detail, I mean, here is again this example of this two-dimensional Bogoliubov Fermi surface. It's such that in this outside region, outside of the blue region, the Pfaffian is positive, which I will discuss a little bit more, how to calculate it and why it is positive. And it turns out that inside the Bogoliubov Fermi surface region, the Pfaffian is negative. That means that in between you have to have a crossing of the quasi-particle energy and therefore a line of zero energy excitations. Okay, now coming to the symmetries. So the symmetries of the Hamiltonian to allow this Bogoliubov Fermi surface is that the system has the combination of charge conjugation and parity. So if you write down the unitary transformation that employs charge conjugation and parity, so particle hole and the usual parity, then if the Hamiltonian transforms with a minus sign and has this symmetry, then it's allowed to have an ultranodal state. And then this Pfaffian, which is the square root of the determinant, is a well-defined quantity. You can calculate it. Now to induce a sign change of the Pfaffian, such that in some regions it's positive, in some regions it's negative, you actually need a time reversal symmetry breaking, such that the states and at some k points have this different property that if you multiply the Pfaffians, you get a -1 to the power of L, and L being an odd number to obey the desired property that you have the Bogoliubov Fermi surface. And I mean, this is nothing new. This has been discussed for this model of J equals 3 half pairing in the cubic systems earlier. Now, what we have done is to look at another example where one actually pairs spin 1/2 particles, but uses an additional degree of freedom, namely the two-band nature of some superconductor. And this is the Hamiltonian we worked on. Now this is a 4x4 matrix. So there is a band space, which I denote with tau, and spin space, which I denote with sigma matrices. And what we have is just two bands that are inspired by Fermi surface of iron-based superconductors with some hole pocket at the gamma point and electron pockets at the x and y points. And then we have the intraband spin singlet, the usual order parameter in such a system, which can be sign changing if it's an S plus minus a superconducting state, can also be a constant S-wave superconductor if you want. And then we have two additional ingredients which are needed. One is an interband spin triplet pairing term, denoted by delta 0, and an interband spin triplet pairing term which breaks time reversal symmetry. And that's the needed ingredient to actually be able to tune to the Bogolubov Fermi surface state. Now, these terms, they might be small, but they might be present, for example, being induced by a spin-orbit coupling. If you have a usual pairing and have a system with some small spin-orbit coupling, you automatically induce some triplet components and might also induce some additional time reversal symmetry breaking terms. Okay, now what we did, we had this Hamiltonian and looked at the properties of the Pfaffian. So you can, for this 4x4 matrix, you can exactly calculate the Pfaffian. Here it is. This is the quantity. It depends on all the order parameters, all the eigenenergies of the bands at the certain k points. And then you have to figure out whether this quantity is positive in some parts of the Brillouin zone and negative in some other parts to figure out whether you get a Bogolubov Fermi surface. Now, as a simple approach, you can minimize this quantity with respect to the eigenenergies and look whether the minimum is actually positive or negative. Now, if you think about far away from the Fermi surface, then you can prove that the Pfaffian is actually a positive number. So it's sufficient to find one single k point where the Pfaffian is negative, and then in between you need to have the Bogolubov Fermi surface. And now this condition for having a minimum that is negative is given by these two properties. So first, if the usual order parameters are both positive, so delta 1 and delta 2, the two order parameters on the two bands in product are positive, then this quantity becomes negative as soon as the delta 0, the triplet pairing, becomes larger than the corresponding singlet pairing, which actually can happen as soon as you have a near nodal or nodal order parameter, because then this quantity can become arbitrarily small. If the order parameter delta 1 and delta 2 have opposite sign, then the condition is slightly different, because then this time reversal symmetry breaking order parameter needs to be larger than this product. But again, close to the nodal points, this condition can be easily fulfilled. Okay, now the question is, so far we have just put in the order parameters and played around with finding Bogolubov Fermi surfaces and so on. Now the question is, can you actually stabilize such an exotic superconducting state? And to go in this direction, we first did a simple calculation. This is a calculation where we have some triplet pairing and ferromagnetic fluctuations only, and then later we added a singlet pairing in a multiband model. So as I said, here is just a standard Hamiltonian two-band model, two parabolic bands with two different masses, some magnetic interaction, ferromagnetic fluctuations, and then a triplet nearest neighbor pairing in this system. And if you solved this interacting problem in a mean field approach, then you come up with this mean field equations, and it turns out that the TC of this order parameter becomes larger if there is spin splitting in the superconducting state, and it becomes more favorable if the two bands have actually different masses. And from this, you can then work out the phase diagram. Depending on these parameters, the ferromagnetic interaction and the triplet pairing, you see there is a normal state where you don't get any superconductivity at low temperatures. You get a non-unitary triplet, as you would expect from just a triplet pairing ansatz. But you get also this non-unitary phase where you break time reversal symmetry spontaneously in the superconducting state. So you start from a metal, non-magnetic metal, so the ferromagnetic interactions are not strong enough, go into the superconductor, and then time reversal is broken exactly at the same temperature. And this is just what you see here. And this is a kind of this property of the needed ingredient that you stabilize such a non-unitary triplet state. Okay, now as I said, we include a singlet pairing, so some nearest neighbor singlet pairing to foster also the sign changing S plus minus state. And then the phase diagram becomes rich, so you get an S wave, you get a D wave from the nearest neighbor pairing, you also get S plus ID pairing, but notably you also get phases which are ultranodal, where you actually have the Pfaffian change the sign, and you also can stabilize a phase where the C4 symmetry is spontaneously broken in the superconducting state. So in this case, one would see that if you measure the gap around the Fermi surface, that it's kind of zero, then has a gap, and then stays zero at that angle where you actually have the Bogoliubov Fermi surface, because because you have a Fermi surface, the gap stays zero. Okay, so far to the theory. Now the question is this just some theoretical thought, some theoretical model? Is there any realization? And we claim to see some experimental evidences in some ion-based systems. So this is a compound that we worked quite a bit on. So this is iron selenium, which is an anisotropic superconductor with a sizable TC, has a very anisotropic superconducting order parameter mapped out quite well. But when you add, when you substitute the selenium by sulfur, which is a kind of as putting chemical pressure onto the system, then notably this anisotropic superconductor, which is coming from a nematic phase, this dies out at some certain sulfur content, and it turns out that both the electronic structure here on the right-hand side becomes tetragonal at high temperatures, but also the superconducting state has some interesting properties, as I will discuss in a second. Okay, so now to look at that, we kind of took our model system, so just this Hamiltonian with the two bands, with a singlet pairing and the two triplet pairing terms, and played around with the anisotropy of the order parameter, knowing that in the iron selenium system, it should evolve from a very anisotropic order parameter to an order parameter that resembles a tetragonal state. And that, as I mentioned, then induces a nodal or near-nodal states in the singlet order parameter. And indeed, when keeping these terms, the triplet terms, constant, one can find a sequence of states, A, B, C, D, which go along the sulfur doping content, where from a normal superconductor to a superconductor with a small Bogoliubov Fermi surface up to a superconductor with large Bogoliubov Fermi surfaces can be realized. Where, again, this condition of the minimum of the Pfaffian being negative is fulfilled for some parts in the Fermi surface. Now, what are predictions for these states? So, as I mentioned in the beginning, this ultranodal state has a finite density of states at zero energy. And now, again, here is a calculation from our model for these four different test states, A, B, C, D, where you can see as a function of this sequence, the density of states at zero energy increases because of the presence of the Bogoliubov Fermi surfaces. And exactly this is also seen experimentally. So now here are experiments for tunneling conductance as measured in SDM experiments on the surface of iron selenium and iron selenium sulfur, where here these numbers are the sulfur content as measured. And as you can see, in the pure case, there is no density of states at zero energy, whereas it's not so easy to see because this offset, but it turns out that starting from 17% doping, the density of states at zero suddenly has a jump to a finite value, which is reminiscent of appearing some two-dimensional Bogolubov Fermi surface in the superconducting state. And that property, just to rule out other explanations, should not be a disorder effect because the samples are quite clean. They have quite large residual resistance. They show quantum oscillations. So the simple disorder filling effect might not be the explanation. And as a side effect, there is a sister compound, the iron selenium tellurium, where you replace the selenium with tellurium. Then the same effect is actually not seen. So also the same sequence of measurements with different doping content was done. Also, this compound has this property that the nematic order goes down as a function of doping, but it was not found that any zero energy density of states is measurable in STM. Okay, some more consequences. The finite density of states at zero energy gives a finite specific heat at zero temperature. So here is a calculation of CV over T as a function of temperature. So red is a normal state, just normal metal. And then A, B, C, D are again the sequences of our test states where A doesn't have a Bogolubov Fermi surface. You just see the normal jump of the specific heat, and then the specific heat divided by T for T going to zero goes to zero. However, for the states with Bogolubov Fermi surfaces, you acquire a finite density of states. And therefore also a finite specific heat at low temperatures. And exactly this is also measured on the iron selenium sulfur compound. So again, for a small doping, 0, 0.08, 13, the specific heat goes to zero at zero temperature. But for a 20, which is beyond the transition into the ultranodal state, it seems that there is a finite specific heat if you extrapolate to zero temperature. Again, a signature of a possible Bogolubov Fermi surface. Then I mentioned this C2 symmetric superconducting state, which we could stabilize with our model, with our two-band model with singlet and triplet pairing. And exactly this property that at some angles you have a zero gap and then some finite gap with some C2 symmetry. This was exactly measured also in the iron selenium sulfur system with an APRES experiment. So here you see the gap seems zero, finite, and then zero in some angle regime. So in this regime, no pullback of the spectral function as a function of lowering the temperature below TC is seen. Okay, some more predictions or consequences. And let me mention that the property of Bogolubov Fermi surfaces has been discussed in the literature some time ago. One example is actually a simple D-wave superconducting in a Zeeman field, because for D-wave superconductor, you also have the nodal regions. And if you now apply a simple Zeeman field, then these Dirac cones close to the nodal regions, they are just getting shifted. One is getting shifted down, the other is getting shifted up, and then making space for actually a finite region of zero energy excitations, which is just the Bogolubov Fermi surface. But here in this work, some time ago, it was actually shown that the D-wave superconductor, despite having this many low energy excitations, is actually a stable state just in a simple single band model. Now, the same thing we also observed in our model, namely that whenever a Bogoliubov Fermi surface appears, the superfluid density actually gets suppressed. And what we did, we just calculated the current correlator for this mean field model in PCS theory and saw that the superfluid density is getting suppressed. And here you see just a tuning of this triplet order parameters, where once you reach the shaded region, then some of the quasi-particle bands touch the Fermi level. You enter the phase with the ultranodal state, but still you see that the superfluid density stays positive. If you do another touching, then it turns actually out that you get a negative superfluid density, which would mean that this system would be unstable thermodynamically. Now, experimentally, there are also some evidences that this is actually happening in the iron selenium sulfur system, where, here I show you some data on the inverse penetration depth, which is proportional to the superfluid density as a function of sulfur doping. And now note that the experimental data points, they are constant or rather go down once you reach the ultranodal state. And this blue curve here is actually a possible calculation of the expected density or the expected superfluid density from data where you obtain the effective masses and the Fermi surface in quantum oscillations. So you know what is the expected superfluid density. However, it seems that there is a reduced superfluid density compared to the expected one from the electronic structure. So another evidence that this could be a ultranodal state. Okay, then one more thing which we worked on recently. This is the property of spin relaxation. A nuclear spin relaxation rate as measured in NMR experiments. And here I have just put up some data from aluminium from the early days. So at high temperatures, you have a constant spin relaxation rate. Once you hit TC, then there is this increase, this Hebel-Schlichter peak. And then once you reach low temperatures where there are no quasi-particles available, then the spin relaxation rate actually goes to 0. A similar thing was also recently observed in Kagome systems. So this will be the only reference to Kagome systems in my talk, where there's also a Hebel-Schlichter peak. Probably you will hear about more on that tomorrow by Brian's talk. Now, here is, for this Hebel-Schlichter peak, there is the focus on the behavior close to TC, where you actually look at this property of this coherence factor and then can distinguish S-wave and D-wave states. I want to focus a little bit on the low temperature behavior, because at low temperatures, the presence or absence of quasi-particles makes a difference. And then is the question, what is actually happening once you enter the phase with the Bogoliubov Fermi surface, where you have a lot of low temperature excitations? What is happening with the relaxation rate? And for this, we looked at the imaginary part of the susceptibility. We took our model, put in the stabilized order parameters for a Bogoliubov Fermi surface. So again, this is a two-band model, two parabolic bands. Here the colored is just the Bogoliubov Fermi surface, which in this case is a C2 Bogoliubov Fermi surface. And then we calculate the susceptibility from this model. Okay, what do you see? So first, let's look at the case without interactions. Then we obtain exactly this result, this turquoise. So there is, first of all, there is a finite value at t going to 0, as expected, because we have low energy quasiparticles in the ultranodal state. But then once you add interactions, and we just did just some Hubbard model calculation where we did some mean field RPA calculation of the susceptibility in the superconducting state. And then you see it's possible to obtain actually an upturn at low temperatures. And that is a property from the states at low energies. And here red, green, and blue are actually states of similar nature. So, zero energy states that have similar eigenvectors. It's a 4x4 matrix, which you need to diagonalize, so the eigenvector is a little bit more complicated. But we believe that in the ultranodal state, you can induce some nesting feature, which actually can be enhanced by correlations. And that is exactly also seen experimentally. So the red dots are actually a data from an experiment where whenever you cross the doping range where we believe there is an ultranodal state, you see an upturn in this spin relaxation rate, which is a very unusual property for a superconductor. Okay, let me give here a small overview of some of the Hamiltonians that can give rise to an ultranodal state. So there was this 3½ J equals 1/2, 3½ superconductor, which was discussed some time ago. Our model of a two-band time reversal symmetry breaking pairing state. I mentioned the D-wave superconductor in the Zeeman field. You can also look at loop currents and a D-wave superconductor. We will also get Bogolubov Fermi surfaces, or you can work with a broken time inversion symmetry, which gives a mixed parity superconductor. Okay, the chairman is already standing, so let me just flash this summary slide here and mention my collaborators. So this was done together with Chandan Sethi, Yifo Kao, Laura van Valero, Shinibali Bhattacharya, and Peter Hirschfeld. And with this, I thank you for your attention, and I'm happy to answer any questions.
Thank you. So we are ready to...
Hi, very nice talk. Thank you so much. I have a question about the iron selenium sulfur.
Yes.
There are recent results of STM that they see Bogolubov quasi-particle interference, and they claim that they have nodal gaps, but the nodal gaps are due to the nematic fluctuations, that is, superconductivity is mediated by nematic fluctuations.
Yes, I'm aware of this this alternative proposal. I think I have also in. I think I cut it down. But there is an alternative explanation for the nematic fluctuations, where they believe that the specific heat goes down extremely quickly at low temperature. So you cannot see the finite value of the specific heat because you cannot measure to low temperature, because the nodes are very, very steep and therefore giving rise to extremely small or extremely steep density of states at zero energy. But yeah.
So my question would be, in your model, if you take out with magnetic fluctuations and put nematic fluctuations, would you still get ultranodal states, ultranodal superconducting states? Or?
Well, I mean, to stabilize, I would argue that in principle, let me just, where is the model? This one. So, I mean, I think here the main ingredient is just the magnetic fluctuations and this triplet pairing. This you need, otherwise you don't get Bogolubov Fermi surface, because you need the time reversal symmetry breaking. But for the ordinary type, I mean the interband pairing, we have just, I mean, here is just a phenomenological model. So whether this comes from spin fluctuations or whether it comes from some other boson, that might not play the major role. So the answer, yes, maybe, but we have not tried because we have put in here the harmonics that you would get for a spin fluctuation calculation.
Okay, thank you.
I just have two very quick questions. So first, correct me if I'm wrong, I think there's no difference, there's no notion of states inside the Fermi surface, the Bogoliubov Fermi surface being filled and the ones outside being empty. Is that correct?
No, there is no notion.
Okay, because the negative energy and positive energy are the same excitation.
Yeah. So in a sense, I mean, you can think about this cuprate analog. So you have just the quasi-particle bands,
yes,
which then are getting shifted. One is shifted down and one is shifted up.
Right.
And the CP symmetry, that guarantees that the two bands, they just intersect. They don't hybridize. And then you obtain the zero energy excitation.
Got it. And the other thing is, have you looked at vortices? I mean, like, for instance, the Abrikosov lattice, maybe it's very different here when you have Bogoliubov Fermi surfaces.
We have not looked at that. Could be an interesting property.
Okay, thanks.
I have a question. The triplet order you have in iron, selenium, sulfur, you need some triplet component, right?
Yes.
Why is that spin orbit induced, or?
Well, one possibility is it's spin orbit induced. You have I mean, if you believe in normal spin fluctuations in a system with spin orbit coupling, then if you transform to the pseudo spin, do the pairing, and then transform back to the normal spin, you automatically get some triplet component.
Okay. Did you guys try? Did you do that? I mean,
no, we didn't do that. I mean, at that point, at that level, I mean, we were phenomenologically writing down the delta zero and the small delta.
Yeah.
And then the other was just to start from some ferromagnetic fluctuations with some microscopic triplet pairing, just phenomenologically.
Yeah, okay. Okay, and the last question, the upturn in your relaxation rate in the very end,
yes.
Is that some kind of instability of your Bogoliubov Fermi surface, or can one not talk about that?
I would not talk about that as an instability, because, I mean, okay, we work very close to the critical U, but that's the standard of kind of RPA calculations. But we believe this comes from this unusual nesting of these green states, which are just mixed states of spin up and spin down and the band 1 and band 2. And they, I mean, you do 64 by 64 RPA calculation, and we believe they do exactly lead to this enhancement. But we have seen this in several parameter regimes. I mean, in the paper we have a C2 symmetric Bogoliubov Fermi surface, which shows the upturn, and we also have a C4 symmetric one that also shows this upturn. So we believe it's kind of generic.
Yeah, any other questions?
Oh, thank you. So last part of their talk, the spin relaxation rate, so this could be like static response, right?
No, it's dynamic response. So I was putting this a little bit under but it's the imaginary part of the susceptibility at finite frequency, but small frequency. That's usually the Lama frequency of the NMR experiment. I mean, technically we calculate the susceptibility at finite frequency and take the imaginary part.
And in this kind of system, is there any special collective mode apart from the usual superconductor?
You're talking about some properties of
fluctuations.
Bogoliubov Fermi surface fluctuating. Possible, but we don't have this dynamics in our calculation.
Mm-hmm.
Yeah. So you showed a slide when you use the Pfaffian to kind of distinguish between positive, negative, and trivial, non-trivial. So I mean, the system is gapless, but this looks so much like what you use for Majorana. So is there any notion of topology really?
Well, I mean, okay, it's a big question. I mean, it's not, there are no Majorana because you have a gapless system. So there, it's not this notion of topological protection of any quasi-particles. But all what I'm saying is that the presence of the Bogoliubov Fermi surface, by changing any parameters, it will not vanish immediately. So it will, I mean, if you change the magnetic field, the pairing, the band structure, the masses, whatever, it might shrink or increase slightly. And then if you change them eventually by a large amount, you can remove it. In that sense, it is kind of protected by this C2 invariant. Well, yeah.
Please. Okay, maybe I missed some part of your talk. So you work with two-band model and ferromagnetic fluctuation,
Yes.
and then you pick up the ion selenide or telluride, your candidate system. So I don't quite, I mean, so as to me, this system is more than two-band system, and also its fluctuation is not very much close to the...
So if you look at this model, indeed, there is only, at this point, there are only two bands, two whole bands. But we believe, and let me say it like this, the appearance of the Bogoliubov Fermi surface happens whenever you have two bands which are very close in energy. And if you think about the band structure of a generic ion-based superconductor, then closeness of two bands only happens close to the gamma pockets. Because if you go to the X and Y pockets, then the other band is far away. And then you would need a huge order parameter and huge time reversal symmetry breaking pairing. So therefore, we believe the important physics is only happening close to the gamma pocket. And that's why we only focused on the gamma pocket. You can add another kind of band here with also some pairing, but then when calculating the susceptibility, there will be no contribution. It would be just somehow take the result we have and then add to the spin relaxation rate the result of a standard S plus minus superconductor, which goes down, and then you add it up. But if the upturn at low energy is strong enough from the Bogoliubov Fermi surface, you will still see the upturn.
How about the ferromagnetic fluctuation? It's also...
Well, there are some experiments that claim ferromagnetic fluctuations in this iron selenium sulfur. And there is also, one has to take this a little bit with salt, there is also a MUSR experiment that sees some time reversal symmetry breaking, but I wouldn't put too much weight on that.
Okay, thank you.
So can I ask, maybe this is very stupid because I'm not in this field, but usually if you put an impurity in, because of the presence of the Fermi surface, you get all sorts of interesting Friedel type oscillations. Mm-hmm. What happens here in the presence of the Bogoliubov Fermi surface? Is there some another type of Friedel oscillation that comes out?
I would argue you get bound states.
Oh, okay.
Standard ones, but that is more the physics of the ordinary order parameter, because we start with the S plus minus order parameter, which at, let's say, higher energies, I mean, higher energies of the coherence peak are the dominating properties of the quasi-particles. And we have not worked on that, but there is a work on properties of disorder in Bogoliubov Fermi surfaces, and then you get also an increase of the zero energy density of states if you put impurities. But that's an effect from just this zero energy Bogoliubov quasi-particles.
Any other questions? Maybe I can ask a quick one, Andreas.
Yeah,
So just very fundamentally, I was just trying to understand. So you get this C2 symmetric
Yes.
region in the phase diagram, right? So from very elementary group theory kind of a perspective, why does it allow a C2 solution?
Why does it allow us?
I mean, your parent Hamiltonians, I mean, should I think of it as the allowed state in the parent Hamiltonians irreducible representations still?
Yeah, I mean, as you can see, this is very close to the S plus ID.
Okay, but it's still a square lattice type of.
It's a square lattice, but I mean, in principle, let's go away from Bogoliubov Fermi surface for a second. There is also the possibility of the S plus D instability.
Accidental degeneracy.
Sorry?
Accidental degeneracy?
No.
Okay.
I mean, okay, if it's accidentally, I mean, here it's kind of S and D touch, and then you get the S plus ID. But there might also be the possibility of the S plus D, which does not break time reversal, but breaks the C4 rotation. And here, I mean, in this case, the C2 ultranodal, you actually condense the S wave order parameter and the D wave order parameter at the same time. And that is kind of obtained from this additional ferromagnetic interaction. So you break time reversal, but then it turns out not the superconductor itself breaks time reversal, but also the band shift
Okay.
at the same time.
Okay, so yeah, love to discuss more
Yeah.
later. Okay, thank you.